May-June 2022, variant 3.5. Iodometric titration, question number 2. In question 1, you found the value of X in the formula of basic copper 2 carbonate, which is this. You will now use another method to find the value of X. Copper 2 ions oxidize iodide ions to produce iodine first, and then the amount of iodine produced can be found by titration with aqueous thiosulfate ions, according to this. The chemicals given here are Fa3, which is copper 2 plus containing salt and is made by reacting 10.4 grams of this basic copper 2 carbonate with excess dilute sulfuric acid and making the solution up to 1 decimeter cube with distilled water. Fa4 is 0.1 molar sodium thiosulfate. Fa5 is aqueous potassium iodide, and Fa6 is starch indicator. Apparatus and chemicals given here are a pipette filler with 25 centimeter cube volumetric pipette and a burette with Fa3, Fa4 and Fa5 aqua solutions, a starch as an indicator with dropping pipette, a conical flask with a funnel, and a retort stand with white tie. Moving on to the method, the first step is to fill the burette with Fa4. So we will fill this burette with Fa4, but before we start filling, remember, check whether it's closed or not by rotating it to the right hand side or clockwise. Then heat a funnel on the top to fill the solution, and then start pouring this Fa4. One more thing to remember here is this column, which is below this burette, has to be filled also. Therefore, open it once and remove all the air, filling the solution, and then again add the Fa4 solution to 0 mark. So we will again add up till 0 mark. If the solution becomes excess, you can remove by taking the solution out from here until it reaches 0 mark. Now hold this burette into the clamp in the retort stand. .00 is the reading of burette now. As we know that the least count is 0.1 cm cube, therefore we will record the burette readings up to 2 decimal places. So 0.00, or we can say 0.05. Now the next point says pipette 25 centimeter cube of Fa3 into the conical flask. To use pipette, remember, pipette has 2 ends. One is this broader end and the other one is this narrow end. This is the upper side of the burette, where there will be a mark on this pipette. There will be a mark. Up till here, if you fill the solution, it will reach up to this 25 centimeter cube. So we will attach a pipette filler first, and a pipette filler is attached this way, that it holds the pipette. You can use it through one hand. Now press this button, the upper button A, and squeeze so that this pipette filler will remain deflated. And when you have to fill the solution, like for example we have to take Fa3 in our case, we will put this pipette in the solution and we will press this S button. S button stands for the suction. So let me fill this solution here by pressing this S button. Fill up to the mark and then now transfer this into the conical flask. Keep it as low as you can, because if you drain it out from the upper side, it will splash to the walls and the drops will stick on the walls, which will not take part in the titration. So now press this E button and it will drain out the solution. The next point says rinse the 25 centimeter cube of measuring cylinder with approximately 5 centimeter cube of Fa5. Discard the solution used for rinsing. Then use 25 centimeter cube of measuring cylinder to add 15 centimeter cube of Fa5 and excess of potassium iodide to the conical flask. The solution will turn brown because of iodine formed. Now let's rinse this 25 centimeter cube measuring cylinder with 5 centimeter cube of Fa5 first. So this is our 5 centimeter cube Fa5 and we will rinse thoroughly to the wall, and while throwing it out I will revolve it and slowly I will drain it out so that it will touch all the walls. So the walls and the base all is rinsed with the Fa5 now. Now let's take 15 centimeter cube of Fa5 into this measuring cylinder. So it is 15 centimeter cube now. This 15 centimeter cube is transferred into the conical flask and the contents will turn brown. So they are brown now. Let's move on to the next part now. Add Fa4 from the burette until the mixture changes to pale brown, and then add approximately 10 drops of Fa6, which is a starch indicator. The mixture will turn blue-black. Continue adding Fa4 from the burette until the blue-black color disappears to leave an off-white solid. This is the end point of titration. So we have recorded the initial burette reading as 0.00 and we will continue our working up till here. Then the final solution contains off-white solid. We will observe the end point. Let's start adding Fa4 from the burette until the solution becomes pale brown. So it is dark brown now. And now it's pale brown. We will add 10 drops of starch indicator. Starch is used as indicator so that the color change is clearly observed. If we perform this titration without indicator, it will again work. The white precipitates we have to look for. So now let's wait for this blue-black precipitates to turn completely into white. And that's it. You can see the contain white solid. our endpoint reading on burette is 26.20. Now I have recorded the rough titration results, and both the burette readings must be recorded in the space below. So the initial burette reading and the final burette reading both are recorded, and the rough titer is here. Now let's move on. They say carry out as many accurate titrations as you think necessary to obtain consistent results. Consistent results means ideally the endpoint must have the same reading, same volume consumed every time you repeat the titration. But if your work is not accurate enough, you can go up till a max of 0.10 cm cube apart from two consecutive readings. So accuracy and the consistency is here. So we have to repeat the experiment now for accurate titrations, and we need to get two titers which are not more than 0.1 apart from each other, and we will record our burette readings all in this space provided. So I have made here a proper table in which we have to record all our final initial burette readings and subtracting those two values, the volume of Fa4 used and the best titration results, which means not more than 0.10 centimeter cube apart readings. Now let's start our accurate titrations. Before starting our accurate titrations, we need to wash this with tap water and make sure it's completely empty. You need to wash it like this 2-3 times, rinsing complete. It will give you a clear flask. Now it's ready to be used. Now let's take again 25 centimeter cube of Fa3 first. Transferred to conical flask. Again, add 25 centimeter cube of measuring cylinder to take Fa5, that is 15 centimeter cube. So again, this is our 15 centimeter cube, and the content will turn dark brown. Before we continue with the titration again, let's refill the burette also. So to refill the burette, always try to take the burette out from the clamp and fill it from your eye level, so that you will not have any hazard of overflowing the solution or breaking the burette. Now this time it's not necessary I take the reading up to 0. I can take 1, 2, something like that. So I have taken in between 0 and 1. Let me show you the burette reading also. So the burette reading is 0.60 centimeter cube. Now let's start adding solution from the burette until the content goes light brown or pale brown. And now the content are light brown in color, or pale brown you can say. Let us add 10 drops of starch again. Ten drops of starch, and the solution turned blue-black. Now for accurate titration, we need to add solution slowly in such a way that it will be drop-wise addition, and we will continuously swirl this flask. Do not panic, do not add quite faster because it will disturb or destroy your accurate titration. Be calm and keep adding drop-wise until the content goes white or off-white precipitates are formed. So it's changing its color now, turning into lighter shade slowly. I will close it as soon as it turns white. That's it. So this is our end point. We will record the reading now. Now let's record the end point. And the end point is 25.80 centimeter cube. So I have recorded the readings, final and initial. Now let me take out the volume used by subtracting these two values. 25.20 is the accurate titration result. 25.220 is one of the accurate titration result, which is actually lower than this rough titration, and is always the case. Rough titration will be a bit bigger than this accurate titration value. Now let's repeat the experiment to get the consistent result. Upon repeating the titration, I got a titer value of 25.40 second time, but this was 0.2 centimeter cube apart from the first one. Therefore, these two are not consistent. So I needed to perform the titration one more time, where I got a titer value of 25.10. Now, in these three titration results, I can see that these two titration results are 0.1 centimeter cube apart. So these will be termed as best results, and they will be used for further calculations. Now let's proceed on to the next part. From your accurate titration results, calculate a suitable mean value to be used in your calculations. Show clearly how you have obtained the mean value. Now, from the previous part, if we see, our titration results were 25.20 and 25.10. So we need to take average here. Therefore, we will show here clearly 25.20 and 25.10 added together, divided by 2 to get the mean. So here is the average, 25.15. Remember, if we are getting 2 decimal places value, we cannot round it off here like 25.2. No, because 25.20 gives priority to one of these values. Therefore, we have to write 15. It cannot be rounded off to 25.2. This is 1 mark. Now, let's move on. Calculations. Give your answers to C2, C3 and C4 to the appropriate number of significant figures. Now, all the values below needs to be given up to minimum of 3 significant figures or for accurate calculations we follow 4 significant figures, and here is a separate mark for this. C2. Calculate the amount in moles of thiosulfate ions present in the volume of Fa4 you have calculated in B. So the volume we have calculated in part B was 25.15 centimeter cube of Fa4, and we need to calculate its moles. So with the volume of solution, if we get the concentration, we can calculate the moles according to the formula. Concentration is equals to amount in moles divided by the volume in decimeter cube. So if we have the volume, which is 25.15 in centimeter cube, we can use it here by dividing by 1000. So let's see where is the concentration of Fa4 given in your question. So let's move back to the previous page, and it says here Fa4 has 0.100 moles per dm cube concentration. So we will use this concentration here. 0.100 is the concentration. Moles needs to be calculated, divided by the volume we have calculated, 25.15 centimeter cube, therefore divided by 1000. So in this way we can calculate the moles of thiosulfate, and the value is 0.002515. Now let's move on to the next part, which says use your answer to C2 and the equations for the reaction involved to calculate the moles of copper 2 ions present in 25 centimeter cube of Fa3. So if we have moles of thiosulfate and we have to use equations to calculate the moles of copper 2 plus, so let's go back and see what's the relationship of thiosulfate with copper 2 plus. So on the previous page they have given you 2 equations, and in one equation thiosulfate ions are not directly related to copper 2 plus, and in the first equation there were copper 2 plus, but it's not again directly related to thiosulfate, because the reaction was happening in this way that copper 2 sulfate was forming some iodine, and then that iodine was actually reacting with the thiosulfate. So we have to relate in 2 steps that how many moles were related to thiosulfate with iodine, and then the moles of iodine with copper 2 plus. So thiosulfate to iodine ratio, then iodine to copper 2 plus ratio. So let's apply this here. So if we have S2O3 2 minus thiosulfate ratio with iodine, it was 2:1. Therefore the moles of thiosulfate we got here 0.002515 will give us the half moles of iodine, and the moles of iodine will be calculated here as 0.001257 moles of iodine. Now when I relate the moles of iodine produced with the copper 2 plus, it's again 1:2. So iodine to copper is again 1:2. Therefore 0.001257 moles of iodine will again be doubled to get the moles of Cu2 plus. So the value here will be 0.002515 again. So 0.002515. Now the next part says hence calculate the amount in moles of copper 2 plus present in 1 decimeter cube of Fa3. So these were the moles of copper 2 plus in 25 centimeter cube, and now they have asked you to calculate this number of moles in 1000 centimeter cube, because 1 decimeter cube is equals to 1000. So we will relate it easily. 0.002515 moles are present in 25 centimeter cube. So 1000 centimeter cube will have how many moles of copper 2 plus? So in this case, we will get the value of copper 2 plus, that is 0.1006. So 0.1006 moles are present in 1 decimeter cube. Moving on to the next part. The next part says, use your answer to C3 to calculate the mass of copper 2 plus ions in 1 decimeter cube of Fe3. So if we have the moles of copper 2 plus and we need to calculate the mass of copper 2 plus, so we can use the formula moles is equals to mass in gram divided by the AR of copper. Now the moles are 0.1006 and the mass needs to be calculated, divided by the AR of copper in the periodic table, 63.5. So the answer here is 6.388 grams. Now let's proceed on to the next question. The next part says, formula of basic copper 2 carbonate is CuCO3.x times copper hydroxide. Write an expression including X for the mass of copper 2 plus ions in 1 mole of this basic copper 2 carbonate. So how much copper is present in this formula? So if we want to calculate, the moles are X moles here and 1 mole here. So total moles of copper in this formula are 1 and X. 1 and X. And if we want to calculate the mass, so this much number of moles multiplied by the AR of copper, which is 63.5, we will get the mass of copper 2 plus in this. So the mass will be 1 plus X times 63.5 grams. In terms of X is the mass given. Now let's move on to the next part, which says the formula of basic copper 2 carbonate is this. Write an expression including X, again in terms of X they have asked you, for the mass of 1 mole of the whole thing now. So now if I want to write the MR of this whole compound, that will give you the 1 mole. Therefore the MR of this compound will be written in this way. Copper is 63.5, carbon is 12, oxygen is 16 times 3 here, and then all the things are X times, like X times 63.5 here, and oxygen is twice, so twice of 16, and hydrogen is again twice, so 1 into 2. So this is the X. So therefore if we calculate the overall of this, we will get 123.5, and the whole of this makes 97.5 times X here. So we will write here 123.5 and 97.5 X. So this is the mass in gram of 1 mole of this compound. Now moving on to the next part, which says the expression below links the masses of copper 2 ions in Fa3 and in 1 mole. Now the equation they have given you. Using this expression, show how you could determine the value of X in the formula of basic copper 2 carbonate. Now if you have all the values here and you need to calculate X, because all the values we have written previously contains X, so let us see where are those 4 values. Now the mass of copper 2 plus present in the sample of Fa3 was actually calculated in the previous page, and that was here. It was mass of copper 2 plus ions and it was 6.388. So the first value here is 6.388. Now divided by mass of copper carbonate dot copper hydroxide, means basic copper carbonate mass used. So if we go on the first page, we have in the question which says copper 2 plus was made by reacting 10.40 grams of basic copper 2 carbonate. It means the mass of copper 2 carbonate we have used in the question was 10.40. It means here we will write in the denominator as 10.40 is equals to the mass of copper 2 plus in 1 mole of basic copper 2 carbonate. So here this was given in the previous part, and that was the mass of copper 2 plus ions in this was 1 plus x times 63.5. So 63.5 times 1 plus x will come here, divided by the mass of 1 mole of basic copper carbonate. So the mass of 1 mole of basic copper carbonate was this one. So in the denominator we will write 123.5 plus 97.5x. So here if we calculate the value of x, we can get the basicity in our compound, that was x copper hydroxide. So if we calculate all this, we can get it like this: 0.009679 times 123.5 and 97.5 x is equals to 1 plus x, and we divide it by the 63 point. So the answer from here is 3.42, which is approximately 3. So the formula of this basic copper carbonate to given us was 3CuOH2. So here we comes to an end of 17 marks question from May-June 22 variant 3.5.